Hi, everybody, and I am Eric Williams, and I want to welcome you to the final installment of our Parking Structure Durability Educational Webinar Series, proudly hosted by the Concrete Preservation Alliance. Over this four-part series, industry experts have guided us through conversations about inspection and assessment, post-tension system protection, and targeted corrosion mitigation design. And that is for the goal to ultimately provide a practical framework for durable parking structure solutions. Today's session is titled Global Corrosion Protection for Parking Structures, Long-Term Durability by Design. And in this session, we will highlight how engineers and owners can design with durability at the forefront rather than an afterthought. So, if you are new to the Concrete Preservation Alliance, we are a coalition dedicated to promoting best practices in concrete repair and preservation. Our mission is to offer free, accessible, and non-commercialized education, sharing practical knowledge from professionals in the field to support long-term durability and sustainable infrastructure. We extend our sincere thank you to all of our members and supporters worldwide, whose collaboration and dedication make the Concrete Preservation Alliance and educational events like this possible. And if you missed any of our past sessions or webinars, you can always catch those and the replays of these past sessions at our WeSaveStructures.info website. And before we get into our webinar this morning, probably the best part, or one of the best parts of the webinar series, is the participation from the audiences. So we love questions, and please don't hold back. You can please put your questions into the chat. Just make sure to include your first and last name when you post, and we'll be giving away a $100 Amazon gift card to the person who submits the best question. Our speaker will choose a winner following the session and will be contacted by email to claim your prize. So please get those into the chat and throughout the webinar. And speaking of our speaker, let's meet today's presenter, which is Matt Miltenberger, who is the Vice President of VCS Engineering and has over 40 years experience in the concrete industry. He has a Master's of Science in Civil Engineering and from the University of Maryland, but has spent much of his career working in materials, testing, and durability analysis. In his current role, he helps design more resilient infrastructure by supervising infrastructure evaluations for corrosion and concrete material distress, developing cathodic protection designs, and providing durable consulting services. He is a member of AMP and is a certified cathodic protection specialist and a fellow of the ACI. So, Matt, we're looking forward to your presentation today, and I'll throw it over to you. Thank you.
Thank you. So today we're going to talk about global corrosion protection systems, but in the before we get started on that, I want to go over some of the things we've gone through in the previous slides, the previous presentations. Number one is the evaluation of the problem, the evaluation test methods. That was one whole presentation. You should come to the website and take a look at that. That's packed full of knowledge. There's a lot of stuff in there, and I'm just going to hit the high points of trying to define the problem in this presentation. Then after that presentation, there is the targeting of targeted protection systems, and then there's post-tensioning, prestressed corrosion protection systems. A lot of detailed information in those other presentations. So what I'm going to do today is I'm going to talk about what is typically a major rehabilitation project for a parking garage. They're doing a lot of concrete repair because they've come in and they found that there's a lot of problems here and there, and then kind of selecting the right system for that structure. and for the client. And you have to remember the client in that. It's not just a cookie cutter thing, because if the client doesn't want to have a maintenance program, if the client doesn't have an active maintenance program, some of the impressed current systems may not be the best choice. So let's just get started here. I'm going to start with defining the problem, looking at the various distress mechanisms, and then we'll get into the corrosion mitigation systems. So like we said, to start out, we have to evaluate the structure, determine what is wrong, and what is the root cause. The key here is the identifying the root cause of the problem. And normally all these steps are involved. Every project starts with a visual inspection. So you're going to look for rust staining, cracking, spalls, leaking, exposed steel, efflorescence, all that stuff. And you look at the exposure conditions and you try to identify the issues before it becomes too late and you have to replace the structural element. So doing a visual inspection, you want to, identify like this guy right here, he might be a little bit too far gone. This one, we might have, you see these rust stains in one location. That's probably a failed caulking joint up above, and that's just rust coming through the and hitting the bonding plates between the flanges. This one is corrosion, most likely. You see the expansion all the way around. You've got probably some pretty good corrosion going on here. And then here, this is your metal pan decks. They have, when you see the corrosion on the bottom side, there's a lot of corrosion on the top side of these metal pans. So here's the distress mechanisms that we're going to be looking for. We're looking at freeze-thaw and scaling. Anything that cracks the concrete is going to let chlorides in, right? So freeze-thaw and scaling is what we see here. This is a scaling photo. You see here, there's no issue because that's where they stop the coating. Here they have an issue right next to it. It's kind of a problem there. This right here, you have a metal pan deck with shear studs that are too close to the surface. And then you see this crack, which is running parallel to the beam. And just because the beam is stiffer than the metal pans. And so that crack allows water to get into the pan. And then if this is downhill, it will flow in and corrode everything down below it. This photo right here is ASR, alkali silica reaction. That you can have multiple different types of reactive aggregate. So the alkali silica reaction is the most common. You have alkali carbonate reaction, which occurs with microcrystalline quartz in limestone. And then you have pyrrhotite. Pyrrhotite is a iron sulfide mineral that is mostly a problem in the Northeast and, like Northeast Canada and Northeast US. And then you have fire. Now, fire damage is something that happens in a lot of garages. You may not hear about it too often, but cars do catch on fire. Electric cars do catch on fire. And like this one right here was, completely covered with fire. We ended up checking this beam right here, and we found out that it was actually okay, but the concrete cover had cracked completely. Then we have construction defects, and then we get into the the different specific types of defects that are related to different structures, and especially the post-tensioning and pre-stressed concrete are quite unique. So here's the first quiz. What kind of distress is this? Can anyone take a guess? All right, it's freeze-thaw deterioration. What we're talking about here is the surface of the concrete is flaking off. It is cracking parallel to the surface, and it is, chipping away. So all the edges become rounded. You see a lot of exposed aggregate. It flakes off. You can pull it off with your fingers. It's not. It is from the outside in. So in order for you to eliminate or keep that out of, or have that not become a problem, you have to have air entrainment, and you have to have good compressive strength and a low water cement ratio. And with the use of pozzolans, you're probably needing to cure the structure a little bit longer with the supplementary cementitious materials when you do a new job. And what happens sometimes, you'll pour concrete with fly ash in it, and it's not cured long enough, and it doesn't reach its 28-day strength, which is in a moist cure room, right? So if this is what the cylinders say, it's not necessarily what's happening on the structure if it doesn't cure, if it stops curing after like 3 days. So now, next quiz. What kind of cracking is this? Is this structural cracking? You see some vertical cracks here, but you see these horizontal cracks. They're going like that. And then this one down here underneath, right in the middle. What is that? What is that signal? Well, it's alkali silica reaction. What happened on that project? There was a brick paver area with a sand bed that was depressed over top of that elevator core. So rain would come in and sit in that sand and then keep that concrete wet. And alkali silica reaction expands with water. So that triggered the reaction, and the entire length of that parking garage that had the brick paver depression had to be revamped. They had to pull the pavers out and redrain cast concrete in that area and make it drain away from that area. And they had to treat the beams with lithium nitrate. So alkali silica reaction is, expansive chemical reaction that when silica minerals dissolve inside the concrete, and they combine with water, and they create a gel that swells up. And we can't get into a lot of detail here, but the best approach is to not use that type of aggregate in your concrete. Here's another one, is pyrrhotite. And as you can see, it can be really severe. Pyrrhotite is an iron sulfide oxidation reaction. It reacts with water and oxygen, and it creates an acid, and that acid will attack the reinforcing steel and the concrete along these cracks. There's really not a whole lot you can do other than not use that aggregate, and the key is to test for those aggregates up front. You get the total sulfur content, and if it's too high, you just don't use that aggregate. And if it's less than 0.1% by weight, you can accept it. If it's in between, then there's a few additional expansion tests to confirm whether or not the aggregate is going to react. And then we have fire. This is that case I showed you earlier. If you look at the beam, the fire was down here on this end. This is the beam bottom. This is the north face, and here's the south face. And you can see right underneath this area is where the fire was. Well, what we did is once we tested it, this was using impact echo. You get the strength of the concrete surface. When we sounded this with a hammer, the entire thing was hollow. It sounded like just blah. It was terrible. We shored it up, and then we removed the concrete cover because your concrete cover is what makes concrete a fire resistant material, a non-combustible material. So it has to make its way through the cover. Because we had good cover, you can see right here, we had 2 inches of cover on all sides. The concrete cover was cracked, but once we got down inside the reinforcing gauge, the strength of the concrete came right up. So it was down in this region right here. So the strength comes up inside the further in you go. And what happens a lot of times is the concrete on the surface gets cracked when they spray water on it, right? So it shatters, and then your concrete surface, it sounds bad, but inside it may not be. Just something for you to think about. And then if you look at fire, the color of the concrete can tell you how hot it actually got. If you have this pink, red, that's where you start having some problems. And if you have exposed reinforcing steel, the cover's flaking off, you might be at a point where you might have to remove that element or at least repair it, maybe strengthening it. And if it turns buff, there's hardly any strength anymore in the cement. So you're going to have to replace the element. So much for fire. Now, corrosion causes. This is the primary part of the presentation. Chloride contamination is by far the most prevalent. We have carbonation. That is reaction with the carbon dioxide, carbon monoxide in the air. You see this a lot in parking garages that are underground that don't have good ventilation. And you'll see carbonation on all the surfaces that are accelerated just because the cars are coming and going, and the ventilation may not be as good as it should be. And then you have some acidification, which we don't normally see in parking garages, but we included that here as why it causes some corrosion. And leaching, you do see in parking garages, especially along cracks on the roof. You see the top decks, and water goes through the cracks. It pulls the calcium out of the cracks. It creates little stalactites on the bottom of the slab, that efflorescence that people see. It pulls those alkalis out, and it lowers the pH. So it creates a localized attack along the cracks in the joints, just like carbonation would do along those cracks and joints. So the corrosion mechanism is an ion exchange reaction between your iron metal going to an iron oxide or iron cation that releases electrons, and you have oxygen that's dissolved in water accepting those electrons and creating a hydroxyl ion. This hydroxyl ion, it increases the pH, and so the area outside of anode, and this is called the cathode. This is the anode. This area over here has a higher pH than this area. This area will have sometimes an acidic pH. So for a corrosion reaction to occur, something's going wrong here. Okay. There's 4 things, and consider Acme as your what do they call this? Your synonym. So you have anode, you have a cathode, you have a piece of metal, and you have an electrolyte. And those are the 4 elements of a corrosion cell. And so in every corrosion cell, there's an anode, there's a cathode, there's some sort of a electronic path, and there is electrolytic path. This could be concrete, could be steel, could be, this could be the ocean, it could be soil, it could be anything that will transfer ions. And here's what it looks like in reality. When you open it up, you'll see corrosion spots next to cathodes. So you have anodes, cathode, an anode, and a cathode. And then we have this little presentation kind of shows how the corrosion the products swell, and they build up some pressure. Once they build the pressure, that it starts cracking the concrete because concrete is weak, and then you get a spall. When this is how I look at concrete, I kind of look at it from an electrical diagram, because you have your anode and your cathode and your electrolyte. So your anode is around minus 450. Your cathode normally around minus 200, and I'm not sure why the minuses didn't show up here, but the minus 200, minus 450, and the current will flow from the anode to the cathode through the electrolyte and back to the anode. So, you know, there's a little circuit, and you have about a 1/4 volt between them. Now, when you put cathodic protection on, you put an external anode, which in the case of this is a parking garage, looking at it, protecting the piles, and you see that's a soil anode. And then this is a encasement where they use a distributed anode inside the enlargement of the column. And what you're doing here, you have the anode that is at a lower potential. It will release electrons, and your structure is above here, and so you have like about a 1/2 volt battery is what we're doing. And then your electrolyte is the structure resistance, the anode resistance, the wiring resistance, and the monitoring resistance. And you add all that up, so that's a total sum resistance of the circuit. And when you put it all together, here's what you get. Your CP anode is normally going to be, you know, around 1 volt, minus 1 volt. Your passive structure is going to be around minus 200. Sometimes it's positive, and you have this battery that forms, and the current is going to flow onto the structure, and it's going to reverse the current at the structure anode. And you notice this is going to go across this and go back down. Instead of providing this anode providing electrons, it's going to be a net receptor of electrons. And when it becomes a net receptor of electrons, it becomes a cathode. And that's why it's called cathodic protection, because the anode becomes a net receiver of electrons. And then we have our construction defects. And the key here is just keep the water out, right? You know, you have honeycombing, you've got voids. These are all things that cause problems, right? And you've got reinforcement, loses protective alkaline environment because of the water flowing through the honeycomb, water and carbon dioxide. You have low cover concrete, same sort of thing. Water and carbon dioxide are available. It can trigger cracking really quickly because there's low cover. Then you have construction joints. You have reinforcing that goes across those joints, and that is typically how they hold the structure together, but that's a place where salts can also attack the reinforcing steel. So that's an area that you want to pay attention to when you're looking at your parking garage. Look at the base of your columns, make sure they're in good shape. If there's any signs of corrosion, you probably want to address that when you do any kind of repairs. And if there's any kind of embedded piping like electrical conduits, right? That water gets into those and it runs along and it carries salts and there's condensation that occurs inside. So if you have any embedded piping, it can be problematic. And you know, one of the best things to do is just abandon it and fill it with corrosion inhibited grout and put external conduits on the structure, surface mounted. So now we're getting into the corrosion mitigation systems, and let's just look at, for metal deck case right here, we're looking at targeted discrete anode application. What you see here is the low cover. This caused a lot of problems, and this is the crack. This is the same photo I was showing you earlier. Here's a project. You can see the cracks. What this map here is a heat map where you look at the corrosion potential, and these little square dots are where you would put a targeted anode, one of those drilled in anodes. What we're doing is looking through the concrete at the metal pan, and we're saying, oh, there's corrosion in this area of the metal pan. You'll see this crack. You don't see, you know, the surface doesn't look bad, but underneath there is corrosion in the metal pan. And all these right here, these little bigger dots, those are your studs, your shear studs. And you can see the shear studs over here. And you see them here. These are all ones that had low cover. They had like 1/2 inch of cover. And so the icing salt that was put on there created, contaminated the surface down to the tops of these. And the top of the head of these would pop the surface off. Now, this is the top surface. This is the bottom surface. These dashed lines here are places where they would remove and replace the metal. And they would cut a new piece of metal like this, and then they would put that back in and weld it in place to provide the strength, because that metal pan is the reinforcement for this between the girders. Okay, see, this is a girder, that's a girder, that's a girder. You know, this is the girder. These are the purlins. You know, and the metal pan's running lengthwise. So here's how you do it along a crack. You put a string of anodes on one side, a string of anodes on the other side. You attach them to the reinforcing steel on either side and on either end of the string. You don't run it across the crack, because what happens is the wire gets corroded at the crack once the sealant fails. Okay. This is how we protected those shear studs. You drilled a hole in the top of them. We put a rivet in the top, and we wired them over to the anodes. and that was put in all along these. Now, if you do a regular conventional reinforcing, this is a pan joist system that we're removing the concrete repair, doing the regular concrete repair, and you put galvanic anodes in around the perimeter. This is a targeted application. You want to make sure you set up your repair areas so that they're not going to produce additional cracking. So this is from the ICCP technical guideline. And then you put the anodes in. And if you look at each one of these anodes, there's a little ring of protection that goes around each one of those anodes. And think of it like a ball, a little sphere of influence. And that is about 18 inches in radius. So one anode. So you want those spheres of influence to overlap so that you can protect all the area around the perimeter of the patch. And that's what you're doing. And when you do that, you're protecting the inside of the patch. So, this is a very common solution to parking garage repairs. You put the galvanic anodes inside along the perimeter so that they protect that area that's right outside the patch, so that you don't have a secondary halo effect once you finish your patching. Another area of concern is, like I was talking about, the columns. Now, here we had a problem where this is your footer, this is the joint. You had moisture and salt leaking down along the side, and gets into that joint and it starts corroding. And if you notice, it's reinforcing. This is your dowel, and it's right at the edge. It was they bent it in, but it didn't protect it at the base. Right here at this joint, it started to corrode and it spalled the corner off. So now you've got corrosion activity right there, and you got corrosion activity on the other side. What they did here, they put this is called a Galvan mesh. It's a zinc mesh that's embedded into an activating mortar, and then they put it's like a plaster, but an activating mortar that acts as a plaster. It covers the joint really well, and they smooth this off and they paint over it, and most people don't even know that it's been done. And then we look for a global system, the ICCP systems. And what we're doing here is we're going to put mixed metal oxide as one of them. Mixed metal oxide is a mesh anode that's put on the above the concrete surface. You're putting an overlay in, and that's connected to the reinforcing to throw current to it. Now, what happens with this is it protects it. Most of the current is delivered to the top reinforcing steel. That's where you get the chloride contamination. That's where you need it most. But it will also provide some current to the bottom reinforcing, and it'll polarize both layers depending on the thickness of the slab. And there's multiple sizes of mesh, and they have 75 to 100-year anode life. So if you have the system installed and it's running properly, and you maintain the electronics, because electronics fail, wiring fails, this mesh doesn't. So that's embedded in the structure. If the electronics are maintained, you can you prevent corrosion problems in your garage for a very, very long time. And the big issue with the overlays is you're going to lose a little bit of headroom, a couple inches. An inch and a half to 2 inches is pretty typical, and you have some additional dead load. So you've got to make sure your structure is solid enough before you do this. And a typical zone is between 4,000 to 8,000 square feet, and you wire this thing together on the bottom of the slab. Here's a couple pictures of an installation. This is actually a bridge. It's not a parking garage. but this is the entrance to a parking garage right here. This has all been milled, and they did concrete repairs inside. This is a repair to a previous, this is a system that was installed in the 80s, late 80s, early 90s. And they replaced, they left the electronics go. They had short circuits, electronics failed. People retired, nobody knew what was going on. They just shut them off. And, you know, after about 10 years, they had corrosion damage in them underneath. And so they had to repair the corrosion damage. This was the drive aisle where you entered, and you see the barrier here, the head knocker. And this was the main entrance, the main exit on the other side. Both of them were completely replaced because of the amount of damage, but other areas were patched. And here you see what you do is we drill through the structure, and you put your wiring down through the floor, and we use these things called conductor bars. And these little pins, these are what we call Christmas tree anchors. They're push pins. You drill a hole, you push them into the concrete, they don't come back out. The same thing you have in your car, hold in all your the plastic pieces. So you have a rectifier. The rectifier provides current that gets distributed along each sheet. And so you have to look at the current distribution whenever you do these systems, and you have to make sure that you don't have your runs that are too long. You have to make sure you have enough current that makes it to the opposite corner. This is what it looks like in plan. You see the wiring and the soffit. It comes down, goes over to the rectifiers, comes up through the floors to a rectifier cabinet. This is our monitoring system, and that's what the inside of the rectifier cabinet looks like. Okay. This is the wiring as it comes down through the floor. They're looking at the overlay here. What we do is we put a pipe nipple through the floor. You run all your wires through that pipe nipple that's grouted in place. Then you can, you foam the top of this, you get your wires, and then you just mount your box to the bottom. You can see the pipe nipple right here, and it's attached to the bottom. This was a waffle slab, allowing it to be done this way. You use a shallower box on a flat plate. Then we have ribbon systems. This is a system where we cut a slot, and these slots are typically a foot apart. They could be 18 inches, depending on how much reinforcement you have and the size anode. The key for selecting this is make sure you have enough cover. You need enough concrete cover to cut these slots. The slots are cleaned, then they are grouted, okay? And in this case here, there's a parking ramp, and you have a current distributor bar going perpendicular. That's what the ribbon anode looks like. And here's the picture of the guy installing that. Here's another photo where you can see the ribbon is in the slot, and this is where your conductor bar is. This is where you distribute the current to all the ribbons, and then they're filling the slots with grout. It's kind of a messy setup. It is not the most, you can see it, and most of the time these systems are coated with an epoxy or a urethane top coat, a traffic wearing membrane afterwards. And the systems are all wired together into zones, just like the previous photo, previous system with the overlay. You zone it out, and you have multiple zones that are controlled by the rectifier for each zone. Then we have galvanic systems called metallizing. It can also be impressed current, but most of the time it's metallizing. You do this on the Soffit. This is very common for precast because you don't have a lot of cover. A lot of precast, you only have 3/4 inches of cover. You can't use a slot. You have a tendon. You don't want to risk the hitting a tendon with a with a blade to cut a slot, and it's one of the more prevalent systems in around water because it really requires a little bit of humidity. If you're in a moist area, for example, Toronto has used this quite a lot on their Gardner Expressway and underpasses. You metallize the ends of the that's a road, a driveway, but if you a throughway, but if you use it on parking garages, typically you're going to use this on the ends of double T's on the stems because you don't have a whole lot of cover, and you typically have problems at the ends of the double T's because of leaking joints. So here I'm going to do a little video. This is what it looks like. What you're doing is you're melting, you're using electrical, it's like a welder. You have two wires that come together, the two zinc wires or a core spray wire that comes together. They melt, and then compressed air blows these little metal droplets onto the surface. And those are connected. Okay. You make sure you have thickness on here. This is 16 mils. It was probably typically it's a 12 to 15 mil specification. And if you do it at the anchor pockets for PT, that's very common. In precast for the double T's, and a lot of times it's a shorted system, and you can use metallized press current systems as well. This is a structure connection. Basically what you're doing is you're putting a bolt into the reinforcing steel, you patch it back, you put this zinc expanded mesh over top of it, and then you metallize it. It's very simple. It's a very quick, and it's very durable system. Then we do conductive coatings. It's very similar. It's a Soffit system. The key for the conductive coating systems is that you have to isolate it from metals so that you don't short circuit you don't create short circuits. It's a press current system. It's typically a 3-coat system. You're going to use a primer. You're going to do all your surface prep, put a primer on, put the conductive paint, and then put a decorative top coat. And your wiring connections are, to the reinforcement, all that stuff is done before you put your primer on. Here's a layout. What you can see here is you use those little push pins again, those Christmas tree anchors. This is the anode wire that is like a conductive wire. So here we have beams, so they use a conductive wire in between, and it throws current to the conductive coating, which will protect on either side. Here you put typically 15 feet is about as wide as you want to put these wires, and you connect them up to a conduit on the ends. And this is a bond test to make sure the coating was applied properly. You want to do that as part of the QC. You want to make sure your wiring connections are good. Typically, you're having a tight platinized titanium wire that is crimped. Cover it with grease, and then you tape it. It's very, very straightforward. And one of the key things in the installation steps is checking for shorts. This is what's called a Jeep. A Jeep, it allows you to identify low surface metals. You brush that across the surface. It's a high voltage. It's connect. You have one wire that's connected to the reinforcing steel. This Jeep has a high voltage. It's around 10,000 volts. Not a whole lot of current, but it goes across and it will make a spark whenever it comes in contact with a piece of wire or something like that, and it will make this little arc flash, and then it'll you circle it. Normally you have a little burn mark there, and then you fix those. Here's the installation. Put a layer of the coating down. You put the wire in that coating. You put a scrim over top of it. Then you coat over top the scrim. Then you coat the whole wall again. You check the thicknesses, and then you're checking continuity between your wire and the coating, and that's that. And it's really a good system. Galvanic systems, galvanic encasement. This is a bridge deck. It's very similar. I've seen it in parking garages where they do the very similar application. What you're doing here is you're putting a layer, putting the anodes near the top surface once you've milled it, and you're going to protect that top layer of steel from the chlorides that are left over. A lot of times you're going to use hydrodemo. And here's the galvanic encasement. This is another galvanic encasement. And in these cases, you're probably going to get 20 to 30 years of anode life. You're not going to get your 75 or 100-year anodes. You know, they otherwise you'd have very large anodes and it would be cost prohibitive. So you typically get 20, 30 years out of it. You can do an overlay. You must be designed properly. You only have one chance to do it right. Make sure you have somebody who knows who's done this before, knows what they're doing. Typical applications for galvanic encasement are column strengthening, overlays, and here's an overlay example. Basically what happened here, we have a parking garage that's underground, and you had a lot of carbonation on the bottom steel, chloride contamination on the top. They were going to mill the entire top. They're going to basically, they shore this. They put they mill it, remove all the top steel. There's a lot of corrosion damage, potholes and stuff on the top right now. There's still some chloride contamination, but at the bottom, it was carbonated right up to the bottom of the reinforcement. So to save the structure, you put a galvanic overlay in. So they milled off 4.5, 5 inches. They put the new steel in on the top, recast the top. They replaced the HVAC. They updated the HVAC system, you know, what goes along with it, because that's what caused all the carbonation. They weren't venting enough of the parking garage basement. Prestressed structures. You've got I want you to go to the previous webinar. We're running out of time here. I'm taking a little bit too long, but like I told you before, the anchors, the joints are the issue with precast, prestressed structures. If you see water coming in here, water comes in here, it runs down the surface, causes corrosion of the at the midpoint here. A lot of times it's corrosion at the joints, at the ends of the panels, the end of the double T's. Post tension structures, you got to know your history when you get into that. You know, this is a fully encapsulated system, but this is how it's laid out. Typically, you have banded tendons here. So this is your column strip, and then these are your distributed tendons. But you see, they put two of them side by side. Previously, they would lay them out individually. Then they have different systems, like in the 50s, 70s, they were your button heads, paper wrap systems, and they had individual parallel wires. So some of the older structures, you're going to have to deal with that. Then you have the split in the 70s, early 70s, late 60s. They started using a split sheath and the push through greased tendons and 7-wire strand. And then they improved the 7-wire strand in the 80s, and 90s they started using extruded, and today they're using fully encapsulated systems. So it's these old systems that we get involved with. But what happens is this is an opening in a parking garage deck, right? You have to look at the anchors. Really, that's the key. Wherever water gets in, and this is the key area for water to get in. I'll go to the next slide. You can get a blow up. This was the pore strip, the edge of the pore strip. That's the edge of the anchor. You can see there's corrosion here. And the reason we opened this up is because from underneath, you could see there's some rust staining coming from the pore strip joint. And what does that tell you? You have water coming through the joint. All you have to do is, what we had to do was seal these, put a galvanic anode in the patch to protect, because you see, this is the conventional reinforcement. It's in contact with the tails. On the other side, there's the anchors are in contact with the conventional reinforcement. So if you can connect to the conventional reinforcement, you can protect your anchors as well. And then you use coatings, and you use low viscosity epoxy to fill those joints, and then put a membrane over top, a traffic bearing membrane over these joints. Prevent the water, keep the water out, and you're going to be good. And this is what you don't want to see. This is some horror stories. This is a tendon that had corroded so much that it swelled up. It broke the sheath, and it, you see the rust coming out of the sheath. It broke the sheath. The wire looked like it was still tensioned. Here's a broken tendon. You don't want to see that. This is the kind of thing you see with PT that's water into it. And in summary, there's a lot of corrosion mitigation strategies available to repair and protect parking structures. Cathodic protection coupled with barrier systems, penetrating sealers, and proper concrete repair can provide long-lasting repairs. So you have any questions?
Thanks, Matt. And yeah, no, really, really nice job. A lot of information there, and we have quite a few actually came through, and some pretty good ones. So I'll start, seeing what your thoughts are on a couple of them. The first one that came through was, do you see a slotted MMO ribbon systems as more reliable than discrete anode systems for long-term corrosion control, or does it depend mainly on detailing in the installation quality?
Slotted systems coupled with a barrier can last 40, 50 years. So they have longer term, but you have to maintain they have a longer term, a longer life. And the other thing is, you have to maintain them. You have to make sure they're adjusted properly. You got to make sure that the electronics are up to date, and the wiring is always the issue. So make sure when you detail those systems, have your wiring that is accessible. Do all your connections in boxes that are accessible. Do not have connections buried in the concrete. That's one of the biggest problems in the earliest systems, is that they would make connections and they just bury the wires in the concrete, and then you had no idea where the problem was. You couldn't troubleshoot it. I like to use conduit. I can re-pull wire in 20 years if I need to, and maintain the rectifiers every year, which that's the life of, and you can get impressed current systems that can last, indefinitely. I've seen 30, 40-year-old systems that are working absolutely fine because they were maintained.
Excellent. No, I think that answers that. And something going back towards the beginning of the presentation, I believe, and you were mentioning about checking for ASR, and you were doing some aggregate screening as one of the best defenses you can get it.
Yeah.
But would you normally rely on that alone, or would you combine it with things like alkali limits? Or they mentioned GGBS, which I'm not 100% sure what that might be. Matt, you may be familiar with that term.
That's blast furnace slag. Yeah, all those
Okay.
things are all that is. That's a whole other presentation. All right, that's a whole other topic. Concrete mix design is a whole different topic. But yes, all the above. You definitely want to screen it. You got to identify what you're using. You can use low alkali aggregate, low alkali cements with slightly reactive aggregate, and that will be okay. Sometimes you have to do the testing. In the context of this presentation, I wanted you to identify that if it is corrosion is your problem, these are your solutions. If you've got other things going on, if you got alkali reactive aggregate, corrosion may not be your biggest problem. You have to be able to understand that all these things have all these distress mechanisms have to be addressed. If you can keep the water out, that's essentially all you're able to do on an existing structure that is affected with ASR. You have to do your best of keeping the water off that structure and keep it out of the concrete. Improve the drainage. You can do an overlay, do all sorts of different things, membranes. But the idea here was, I brought that up so that you could look at those other distress mechanisms and make sure they are addressed as well, along with your corrosion problem. And a lot of times, membranes, traffic bearing membranes, are a very good solution for parking garages, especially the roofs, to keep the water out, and then make sure your drains do not get clogged. They always seem to, you wash down your structure on an annual basis. It's every winter cars drop dirt and salt, and it fills up your drains, so you have to flush them. So
No, very, very good advice on that. And I know we're just running right after 8 o'clock, but there's just a couple more questions and then we'll wrap up. So this one came in regards to when you were talking about protecting the shear studs and inserting anodes. The question that came in about it, Matt, was what's the life of the inserted anodes? And I think we get that question a lot of, hey, will it protect for 10 years, 20 years, 30 years, whatever that might be. But what is the life of the inserted anodes? And this is kind of interesting as well, is how many studs can an anode service or protect at once?
Okay. Studs are connected to a metal deck. The anode doesn't know that it's protecting just the stud. All right, so it's protecting the stud and the metal deck. Remember, I said there's like this little ball that goes around, this little sphere of influence. All the metal that's connected together within that sphere of that anode's influence will get current. So you can't just say this stud gets current and the other stud doesn't, and it just doesn't work that way. The electrons are going to flow, and they're going to find the metal pan. They're going to find the reinforcing grid. They're going to find the metal stud. So in this case, we were putting one drilled in anode for every two studs, because that was the spacing of they were 1 foot apart, and we put the anodes roughly about 2 feet apart.
Okay.
So that was in the project that you saw. Yeah.
No, that makes sense. And I think this is a good follow-up question to this one, Matt, is with the lifespan of the anodes, and this one's specific to the galvanic encasement. They're asking, is it a function, is lifespan of the anodes a function of the amount of corrosion, or, what goes into the lifespan of the anodes? What are the couple of things that you say, okay, this is really going to have the largest effect on the lifespan of the anodes or this system?
Okay. That is a very good question, because you can put more anode in, all right, and make it last longer. Okay. There's an economic part of it. There is a technical part of it. Technically, you can add more add more anode. Okay, each anode will produce a certain amount of current, but it will not. Okay, the anode will polarize the reinforcing steel towards the anode. If you put enough anode into the structure that it polarizes really close to the anode potential, that anode will last really a long time. Okay. And you can get them to go 30 years, 50 years if you put enough anode in, but you have to check not just the weight of anode, because it's not like it doesn't produce current on a consistent basis, right? It starts out at a very high level, and then over time the current will drop off, and that's described in the paper by David Whitmore in Intelligent Design. You look it up in Materials Performance. George Sergi developed this. He's a professor. He works for Vector Corrosion Technologies over in England. He's a retired professor, but he's brilliant, and he came up with this calculation procedure that encapsulates all the data that was collected for 25, 30 years on galvanic anodes. And the high current that is produced in the beginning, if that polarizes the structure, makes your anodes last longer. So you have to do the design to see, where it's going to be. And if you want your anode to last 30 years, it's going to provide protection for 30 years. Your anode probably is going to produce a whole lot more current in the beginning than you need, but it will decay over time, and at year 30 it will still be producing current the way as much current as you need. And quite honestly, I believe it will go longer than that, because early on it polarizes the structure so much that it changes the environment around the reinforcement, so that it's not corroding, and you don't have that current demand forever. I don't know if that all makes sense,
No, I think it was very well said. And I think at the end of the day, too, Matt, what you might be getting to is it's not as simple as just, let's throw some anodes in, right? I would err on the side of talking to someone, a professional like yourself, and playing that role of helping guide or even doing the design. And I know AMP published some new guidelines too that they absolutely should take a professional stance in having these things designed as well. So no, I think
Yeah,
very, very
no,
well
absolutely. Yeah,
Yep.
absolutely. One of the first things that I realized when I started doing cathodic protection design is that if you can polarize the structure early on, the current demand drops dramatically. But if you barely put enough anode in there, you're going to push the anode too hard and it's going to shorten its life. So the same anode can last 10 years or it could last 30 years, depends on what how close together you put them, how much steel, and how aggressive the environment is. So you can use the anodes and to get multiple. So you can't just say, oh, this anode will last 20 years. That's not the way it works. It will last 10 years in one environment and it'll last 30 years in another environment. And typically, if you use the spacing charge that Vector has, you will get your 20-year service life out of that, because those are based on the intelligent design process that Professor Sergi developed.
Yeah, they mentioned earlier. So
yeah,
but no, I very well done, Matt. And I think that's about all the time we'll have for questions today. If Matt did not get to one of your questions and we didn't have a chance to answer it live here, he will go back and be reaching out to you through email correspondence to make sure that we do that directly. So, but yeah, so that's going to wrap it up for us here. So, if you are interested and wanting to chat with Matt further, his contact information will be up here on the screen. Yep, there it is. So yeah, so please feel free to contact Matt directly if you have any additional questions or you just want to chat about maybe a project or something that you have going on. Please feel free to do so. And then, as always, if you wanted to review any portions of this presentation again or share it with others, we will be posting it to our YouTube channel by the end of this week. And all of our previous webinars are also posted there for those who are looking to learn more about preserving the life of concrete structures. So you can find us on YouTube right there, and then all of our past sessions and webinars are there, as well as this one will be there within the next by the end of this week. This is actually the last of our four-part series on the parking structure durability. So, but we do have very exciting news that even though our webinar series on parking structure durability has ended, we have one more session this afternoon and that'll wrap it completely. We do have our We Save Structure seminar tour is back. So if you are in or near one of these cities that's on the screen, please, you can go to the website there and sign up for these 4-hour in-person seminars that go over a little bit of everything concrete repair. And if your city is not on here, please check back, because we are updating that and making sure we're getting as many to as many locations as we possibly can. So check that out and feel free to register as if you're available. So with that being said, that wraps us up for this morning, or if depending on where you are, it might be this afternoon. We really want to thank Matt again for the great presentation and all the knowledge he shares. Always appreciate that, Matt. And thank you to everyone for attending and participating in the chat. We look forward to seeing everyone at future webinar Wednesday events, and let's get out there and save some structures. Thank you.